the intermittent personality of the reciprocating compressor becomes evident when the subject of pulsations is broached. Take a look at the following 3D animation depicting the reciprocating motion of the piston. As you can see here, because discharge flow is interrupted while the piston is on the suction stroke, pressure pulses are superimposed on the discharge system's mean pressure. At the suction side of the system, the same type of interruption is going on, causing the suction pressure to take on a non-steady component. The frequency of the pulses is constant when the speed is constant, which is the most normal condition for a reciprocating compressor. Now, if the frequency spectrum of the pulses is analyzed, it will be found to contain the fundamental frequency and a rich content of harmonics. Actually, when a forcing phenomenon is superimposed on a system with elastic and inertial properties, a resonant response is likely to occur. This is particularly true when the band of exciting frequencies is as broad as the type of system under consideration. The reciprocating compressor gas system meets this criteria. Why is that? Because gas is compressible, so elastic, and gas has inertia, which is its mass. If left unchecked and a resonant response were to occur, the pressure peaks could easily reach a dangerous level. Because the oscillations are waves, standing waves will form, and interference with the valve action may occur, adversely affecting the cylinder performance. While a single low-pressure compressor may require little or no treatment for pulsation control, the same machine with an increased gas density, pressure, or operational changes may develop a problem with pressure pulses. As an installation becomes more complex, such as with an increase in the number of cylinders connected to one header and the use of multiple stages, the possibility of a problem can increase. When an installation is being planned, it is recommended that the API standard 618 be reviewed in exquisite detail. The pulsation level at the outlet side of any pulsation control device, regardless of type, should be no longer than 2% peak to peak of the line pressure, or the value given by the following equation, whichever is less. In this equation, P% is the maximum allowable peak-to-peak pulsation level at any discrete frequency, as a percentage of average absolute pressure. P line is the average absolute line pressure. The objective of this approach is to improve the reliability of the system without having to design acoustical filters. For many systems, this is all that is needed. API 618 contains a useful table that recommends the type of analysis that should be performed based on horsepower and pressure. This table is seen here and is also available in the downloadable resource section. For example, if the horsepower of your compressor is below 75 horsepower and that the discharge pressure falls between 1000 and 3000 psi, then the API 618 recommends that the second design approach, so an acoustic simulation and piping restraint analysis, should be performed to assess the pulsation impacts and whether or not pulsation control elements will need to be incorporated. Now, although these design methods are beyond the scope of this course, a couple of words though on the API standard. The first design approach consists of an empirical pulsation suppression device sizing. This means that pulsation suppression devices are designed using proprietary or empirical techniques to meet line-side pulsation levels required in the API standard and the maximum pressure drop allowed in the same API standard based on the normal operating condition. Acoustic simulation analysis is not performed when using this design approach. The second design approach consists of an acoustic simulation and piping restraint analysis. This method is pulsation control through the use of pulsation suppression devices and proven acoustic techniques in conjunction with mechanical analysis of pipe runs and anchoring systems such as clamp design and spacing to achieve control of vibrational response. This method includes the evaluation of acoustic interaction between the compressor, pulsation suppression devices, and associated piping, including pulsation effects on compressor performance, and an evaluation of acoustic shaken forces in the pulsation suppression devices. The evaluation is accomplished by modeling the compressor system and the piping around the compressor, and then performing an acoustic simulation to determine the response. Finally, the last design approach consists of an acoustic simulation and piping restraint analysis in addition to a mechanical analysis. This method is identical to design approach number 2 with the addition of a mechanical analysis of the compressor cylinder, compressor pulsation suppression devices, and associated piping systems, including interaction between acoustic and mechanical system responses. Both acoustic and mechanical methods are used to arrive at the most efficient and cost-effective plant design. Okay, now the pulsation control elements can have several forms, such as plain volume bottles with baffles, bottles and orifices, and proprietary acoustical filters. The following picture shows an example of a compressor with a set of attached volume bottles, as you can see here. Regardless of which device or element is selected, a pressure loss evaluation must be made before the selection is finalized because each of these devices causes a pressure drop. For those compressor installations where a detailed pulsation analysis is required as per API standard, several consulting companies offer these services. Until the 1980s, the procedures used when a new installation was planned were to include the pulsation study in the contract with the compressor vendor. During the pulsation study, piping isometrics were used to create a model of the piping connected to the compressor cylinders. A representative of the purchaser was required to be present for the study and had to be familiar with the piping requirements for the compressor area. This was necessary so that decisions relative to the space available, the location for the bottles, and the feasibility of piping modifications could be made during the study. The representative helped to expedite the completion of a final configuration for the piping system and bottle location, since the components were disassembled after the study was completed. This method is still used, although much less frequently. Today, with the advent of modern workstations and faster desktop computers, the solution of the differential equations of motion for acoustical waves in piping system has become feasible. In current practice, pulsation design studies using digital computer technology can produce the same results as those obtained with a dynamic simulation on the system. The results from digital simulation satisfy the requirement of the API standard. An important advantage of this modern method is that digital computers have the capability of data file storage. With storage capability and the ability to readily manipulate the data, it is not as necessary to make immediate decisions. piping changes that are recommended for acoustical control can be evaluated in a more comprehensive manner, taking into account safety, cost, maintenance, and operational considerations. Now, an important point to emphasize here is that interpretation of the results and the quality of the design from the pulsation study depends quite heavily on the experience and skill of the analyst performing the study. So, if you are seeking to purchase a new compressor for your facility and are novice at this type of analysis, then you should give serious consideration to use the services of a competent consultant. For quick estimates or field evaluation of existing systems, you can consider the following curve. This curve is not meant to supersede a comprehensive analysis as previously discussed. It should be used in checking vendor proposals or in revising existing installations where a single cylinder is connected to a header without the interaction of multiple cylinders. So, think of this useful chart as a quick rule of thumb to size your compressor bottles or to check your vendor proposal. The curve should be conservative for compressors under 1000 psi and 500 horsepower. The volume bottle defined is of the simple unbaffled type, as seen here. This chart gives the volume size multiplier as a function of the volumetric efficiency for a single or double-acting cylinder. To calculate the discharge volumetric efficiency, you can use the following equation. To calculate the suction volumetric efficiency, you can use this second equation. Recall, these two equations were discussed in a previous video. Once the inlet and discharge volumetric efficiencies are determined, volume bottles for the inlet and discharge may be sized. First, begin the process of sizing the bottle of interest using the appropriate volumetric efficiency. And then, determine the corresponding size multiplier from the chart. For example, for a single acting cylinder, a volumetric efficiency of 0.8 will yield a size multiplier of 13.3, as depicted here. Next, use one of the following equations to determine the piston displacement. Recall, these equations were discussed in a previous section. Here, in the calculation, use 1 for the speed in N to determine the piston displacement for a single revolution. Next, apply the multiplier to the piston displacement per revolution. The product is the bottle volume. This volume can be then used in the next equation that you can see here to calculate the bottle diameter. Finally, to complete the solution for the volume bottle dimensions, you can assume 2 per 1 elliptical heads and use the following relationship to calculate the length of the bottle. The next video is a practice session where we will use the methodology developed here to size suction and discharge volume bottles for a given single-acting reciprocating compressor. In this practice session, we will approximate the size of a suction and a discharge volume bottle for a single-stage, single-acting, lubricated reciprocating compressor. The objective is to minimize the effect of pulsation by using a pulsation control element, which is in our case a simple unbaffled volume bottle. So let's have a closer look. The gas being compressed is natural gas at the conditions highlighted here. Okay, the first thing to do here is to define the suction and discharge volumetric efficiencies using the following equations. Let's start with the suction efficiency. As you can see here, we have all the parameters needed for the calculation. So, substituting for the known values, we find that the suction volumetric efficiency is 0.87. Let's now calculate the discharge volumetric efficiency. Here again, substituting for the known values yields an efficiency of 0.56. Okay, next we need to find the total volume displaced per revolution, then multiply it by the size multiplier, which we will determine graphically in order to calculate the volume of the bottle. In our case, we have a single acting compressor, so the equation that applies is equation number 1. Substituting for the known values and using 1 for the speed in n, we find the value of the piston displacement for one revolution as seen here. Next, using the volumetric efficiencies, we will determine the size multiplier from the volume bottle sizing chart. As you can see here, the suction multiplier is 13.8 and the discharge multiplier is 10.4. The suction and discharge volumes can then be calculated using the following equations. Finally, the bottle dimensions can be approximated using the following two equations for the diameter and the length. The bottle dimensions for the suction and discharge of the compressor are shown here. With these volume bottles placed at the suction and discharge of the compressor at the operating conditions highlighted here, the effect of pulsation should be minimized.